Hello everybody, welcome back. Today we're going to talk more about splay trees. In particular, we're going to tell how to implement your basic search tree operations using a splay tree. So remember, last time we had this idea to design a binary search tree where every time you queried a node, you brought it to the root. And we noted that simple ways of doing this didn't quite work out so well, so we introduced the splay operation, which is a little bit better. Now, there's this problem with the splay operation, that the way that splay trees are built, you don't actually guarantee that the tree is always balanced. Sometimes you'll end up with very unbalanced trees. And when that happens, your splay operation will actually be very slow, because you have to sort of bring your node up to the root 1 or 2 steps at a time, and it will actually take a while. However, you'll note that if I have this long stretched out tree and I splay this leaf all the way to the root, when I've rearranged the tree, it's now a little bit more balanced than it was before. And so when you use the splay operation rather than the sort of rotate to top operation, it's actually the case that you can't have a long sequence of expensive splay operations, because every time you have an expensive splay operation, it will rebalance the tree and make it more balanced. And so if you keep picking really unbalanced nodes, pretty quickly the tree will balance itself out, and then you'll have nice short log n time operations. But this does mean that we're no longer dealing with worst case time. We need to talk about amortized analysis, average case time. And the big theorem that we're not going to prove today is that the amortized cost of first doing O of D work and then splaying a node of depth D is actually O of log n, where n is the total number of nodes in the tree. And we'll prove this later, but using it we can analyze our splay tree operations. And the basic idea is that if you have to do a lot of work and then splay a very deep node, we're going to be able to pay for that work by the fact that the splay operation will rebalance our tree in some useful way. And that will pay for it, and so amortized cost will be only O of log n. Okay, using this, how do we implement our operations? So a splay tree find is actually very simple. First, we find the node in the way we normally would. We then splay the node that we found, and then return it. Pretty simple. So how does the analysis work? Now, the node, remember, might not be at small depth. It could be at depth D, where D could be as big as n. We then do O of D work to find the node, because that's how long a find operation takes. We then run a splay. So we did O of D work, and then we splayed a node of depth D. And so the amortized cost is O of log n for this operation, which is what we want. Now, the idea here is that you're paying for the work again of finding this n by splaying it back to the root to rebalance the tree. And so if the node was really deep, you did do a lot of work, but you also did some useful rebalancing work, which means you're not going to have to keep doing a lot of work. Now, there's a very important point to note here, that it could be that when you're doing this search, you fail to find a node with exactly that key that you were looking for. But when this happens, you still have to splay the closest node that you found in this operation. Because otherwise what's happening is your operation did O of D work, but since you're not doing a splay, there's nothing to amortize against. You actually just spent O of D work. What you need to do is, if you're doing this big, deep search, you have to pay for it by rebalancing the tree. And you have to, therefore, splay whatever node you found, even if it does not have the right key. Okay, so that's fine. Let's talk about insert. Insert, it turns out, is also really easy. First, you insert a node in the same way that you would before, and that's O of depth much work. And then you run the splay tree find. You find the node again, and you splay it to the top. It all works. Now, to get deletes to work, there's actually a pretty clever way to do it. If you splay your node and its successor both to the top of the tree, you end up with this sort of third diagram in this picture. And you'll note that if we want to get rid of the red node, all we have to do is sort of promote the blue node, its successor, into its place. Because of the way this works out, the blue node will never have a left child, and things will just work. So the code for delete is you splay the successor of n to the root. You then splay n to the root. And then we just need to remove n and promote its successor. So we let L and R be the left and right children of n. And basically what we have to do is we need to make R to become L's new parent and L R's new child, and then set R to be the root of the tree. And once we've rearranged a few pointers, everything works. Now, there's one special case here, which is what if n is the largest key in the entire tree? There's no successor. You need to do something slightly different. I'll leave that to you to figure out. Finally, let's talk about the split operation. Now, the split is actually also very nice with splay trees. The point is there's one case where splitting a tree is really easy. It's if the key at which you're supposed to split is right at the root. Because then all you need to do is you need to split things into two subtrees by just breaking them off the root. And so, but with a splay tree, it's really easy to make any node that we want be the root. So what we're going to do is we're going to do a search to find the place at which we're supposed to do our split. Take whatever node we found, splay it to the root, and then we're just going to break our tree into two pieces right at the root. So to see pseudocode for this, we're going to let n be what we find when we search for the x that we're trying to split at. We then splay n to the root. Now, if the key is n's key is bigger than x, we have to cut off the left subtree. If the key is less than x, we cut off the right subtree. And if the key is actually equal to x, well, the x that we're trying to split is actually in the tree. So, I mean, you might do one or the other depending on if you actually want to keep the node in the tree, or maybe you want to throw it away and we just want to return the left subtree and the right subtree. Now, just to be clear, if we want to say cut off the left subtree, all we have to do is we let L be the left child, and we just have to sort of break the pointer between our node n and its left child so that they're now separate trees, and we just return L and n as the two roots. So that's how we do a split. To do a merge, we basically have to do the opposite of this. And the idea is that it's very easy to merge two trees together when you sort of have this element that's in between them right up there at the root. And once again, there's an easy way to do this with splay trees. You just find the largest element of the left subtree, you splay it to the top, and then just attach the right subtree as a child of that node. And then you're done. So, in summary, splay trees, using this, we can perform actually all the operations that we wanted very simply and in O of log n amortized time per operation. And so this provides a very clean way to do this. We've left out some things in the analysis, though. So if you'd like to see really what the math behind how we can show that all of these things work, please come back for the next lecture.